Manage participants. Good morning, everybody. I'm going to start in about 2 minutes. I'm panicking a bit. I can't find my lecture hat. I don't know where my lecture hat is. I'm going to start in 1 minute. Where is it? Oh. All right, I guess I'm gonna have to lecture without my lecture hat. It's very sad. I still have a recap, but I don't have my lecture hat. Okay, make a paper if you have to. You know what? Let me go get another hat. Actually, you know what? I should be able to lecture without my lecture hat. Okay, so let's start actually with just a little preview of what's coming for the rest of the semester. Okay, couple things just about the rest of the semester. So we have 2 weeks left, and I've decided that 2 weeks, you guys have done a great job all semester. I'm not going to do any more PLCs for the rest of the semester. So here's your schedule for the rest of the year. So I'm going to finish up chapter 12 on Tuesday. So just in terms of lecture schedule, I'm going to talk, whoa, I hate when that keeps happening. I'm going to talk about chapter 12 today and tomorrow. And then I'm pretty much going to be done chapter 12. I'm not going to cover angular momentum. Chapter 12 homework will be due on Thursday. And then Friday we'll have a quiz on chapter 12. And it'll be just like the other quizzes. It'll probably be 5 or 10 multiple choice questions. And then next week, only thing that's due is lab 10 is due on Wednesday. And again, you have 3 different possibilities for lab 10. You can either write a formal report, you can get on Zoom next Wednesday and do a 5 or 10 minute video presentation, or you could film your own video presentation and then email it to me. And then on Friday, next Friday, we're going to do our last quiz. I'm only going to cover parts of chapter 15, 16, and 17. So I'm going to spend basically 4 days covering bits and pieces of 3 different chapters. Chapter 15, which is all about oscillations, simple harmonic motion. Chapter 16, traveling waves. And chapter 17, superposition. I'm not going to assign homework or the homework for chapters 15, 16, and 17. I'm not going to collect because I really am just going to pick and choose the most important parts of each chapter, and I'll be specific about what the quiz is going to be on. So I wanted to just stop this before going into chapter 12 and see if there's any questions on what I just said in terms of the upcoming schedule. So no more PLCs this semester. You have chapter 12 homework and quiz this week. Next week, lab 10, and then quiz on selected parts of chapters 15, 16, and 17. Any questions I can answer on that? If not, what I want to do is just recap a couple things about the last few lectures on chapter 12. And then today I want to cover Tork. I may not get through all of it. Questions from anybody? All right, let me do a little recap of important things so far. So this is just the last couple lectures, so a little recap here. Come on. I have to turn off gestures or something for this tablet. Okay, so recap. So one, we were talking about center of mass. Sometimes you'll see this just little cm or com, just to abbreviate it. It's the average position of the mass of an object. If we have a collection of point particles, there's an equation I went through for calculating it. But if we're talking about a regular object of uniform density, usually the center of mass is going to be right smack in the geometric center. So one thing that I want to just touch on today is if I'm talking about an extended object, I'm going to do this problem for you. If I have, let's say, a meter stick, which is standing straight up, and I let the meter stick fall, and I want to know how fast is it moving right before it hits the ground. Well, I can use conservation of energy. So this thing is going to rotate, hit the ground. When I use conservation of energy, and I want to look at the gravitational potential energy of an object, if it's an extended object and not just a point particle like we've been dealing with, the point that you want to look at is the center of mass. So for the center of mass, you're going to use the center of mass to calculate gravitational potential energy. So it would be mg, and it'd be the position of the center of mass. So for an extended object, if I want to use gravitational potential energy, the point that I'm looking at is the location of the center of mass of the object. So that was the first piece. Second thing we looked at was rotational kinetic energy. So rotational kinetic energy. So if an object is not moving through space so that its center of mass is staying where it is, but it's just rotating, a rotating object has kinetic energy just associated with the rotation. And the equation is 1/2 times I times omega squared. I is what's called the rotational inertia, moment of inertia. It's in essence the equivalent of mass for rotations. This is something that you're just going to basically look up the formula. I gave you a few basic ones that we're going to use all the time. For pulleys, moment of inertia is 1/2 mr squared. For a sphere rolling, it depends whether it's a hollow or solid sphere, but just something you're going to look up. And then omega is the angular speed, but what we're going to see is that's related to my translational speed by v/r. And so what you usually end up doing with this kinetic energy rotation term is you replace I with some number times mr squared. Like I said, for a disk, it's 1/2 mr squared. For a solid rolling object, it's 2/5 mr squared, and so on. You end up replacing you end up replacing omega with v/r. And this 1/2 I omega squared term generally ends up being some number times mv squared. And I'm going to do an example like that in a second. And then we talked about kinetic energy of rolling. If an object is rolling, a rolling object is a combination of just the center of mass moving through space, which has kinetic energy 1/2 mv squared, just the rotation about the center of mass, 1/2 I omega squared. So if I have an object which is rolling, it has both forms of kinetic energy. So I've got 1/2 mv squared, where this is the speed of the center of mass, plus 1/2 I omega squared. And again, this 1/2 I omega squared term ends up, you convert it into some number times mv squared. And so kinetic energy of rolling, I'm going to end up usually with a number times mv squared. And that's how you do most of these. So let me just do a quick little example problem, because I didn't do any really with just rotations. So one, I'm not going to do this, but you could then use conservation of energy. We've done problems like this where I've got two objects connected by a massless, stretchless spring. Let's just call this M1, M2. And let's just say the pulley had a mass M and a radius R. So we're not considering a massless pulley anymore. And let's just say that this mass M1 was initially at some height y initial. And I just want to know how fast is the system moving right before M1 hits the ground. Now, I'm not going to do the exact math, but initially, if I define y equals 0 for M1 to be right at the ground level and for M2 to be where it is, initially all the energy of the system is just gravitational potential energy of mass M1. So what I could say is my initial energy is just M1 times G times the initial height of mass 1. Then right before mass 1 hits the ground, mass 1 is moving, mass 2 is moving, but the pulley is spinning. And now if we're considering pulleys that actually have mass, we're no longer considering massless pulleys. That rotating pulley has rotational kinetic energy. And so my final energy is going to be the kinetic energy of mass 1 times the kinetic energy of mass 2 times the rotational kinetic energy of the pulley. So what I would end up with is 1/2 M1 V squared plus 1/2 M2 V squared plus 1/2 I omega squared. Now I'm not writing V1 squared and V2 squared because they're traveling at the exact same speed. It doesn't matter if the pulley's massless or not, as long as they are connected by a stretchless rope, they both have to be moving at the same speed. So again, if you were to do this problem, what you would do is, I would, for a pulley, the moment of inertia of a pulley, I treat it as a disk, and it's 1/2 mr squared. And then for the pulley, the rate at which it's rotating is related to the speed of the rope, the tangential speed, and I would replace omega with V over R. And so this 1/2 I omega squared term is going to turn into some 1/2, well, let's just do the rest of this out. So what I get is M1 G Y initial equals 1/2 M1 V squared plus 1/2 M2 V squared plus 1/2 times 1/2 mr squared. And again, this is the moment of inertia of the pulley times V, over R squared. So this little piece right here turns into 1/4 the mass of the pulley times V squared. And now what you can see is I just have one unknown, V, if I were to give you the masses and the initial height and so on. So this is just sort of a generic problem, but I haven't really taught that much about rotational kinetic energy. So if something is just rotating and not moving through space, it has rotational kinetic energy. And if we're talking about a pulley, where the pulley is no longer massless, then it does have a rotational kinetic energy I need to take into account. One more quick little just problem that comes up a lot. Let's say I had a meter stick, the one I was just talking about. And I have the meter stick, which is sitting straight up. And I'm assuming the center of mass of the meter stick is right smack in the middle. Then the meter stick falls. And the question is, what is the speed of a point at the end of the meter stick right before it hits the ground? So, you know, I've got a meter stick, which is somehow hanging or sitting straight up. I let it fall right before it hits the ground. What is the speed at the tip? And you need to be specific, because even though all parts of the meter stick have the same angular speed, different parts have different linear speeds, because remember that linear speed, translational speed, is related to my angular speed by V equals R omega. So the farther you are from the axis of rotation, the bigger the linear speed is. So here, without going through the whole big energy equation, initially, all of the energy is just gravitational potential energy. And again, the point I look at is the center of mass. So here, if I want to know what is the initial height, I'm always, for an extended object, looking at the center of mass. So what I would say is my initial energy is the mass of this meter stick times G times Y initial. And right before it hits the ground, I can consider, you know, the thickness of this meter stick to be pretty small. And so I'm just considering y equals 0 right at the bottom. It is, however, rotating. And so it has rotational kinetic energy, and that's equal 1/2 I omega squared. So in this case, for a, what is this, a rod, a stick with the axis of rotation at the end, I, and again, this is one of the ones you can look up in your book, is 1/3 ml squared, where m is the mass of the rod, L is the length. So what I would see is this equals 1/2 times 1/3 ml squared times omega squared. And what I could do is that, well, let's just do this whole problem. So what I want to know is, right as this thing is about to hit the ground, what is the speed at the end of the meter stick? So what I have is the initial potential energy, and let's just be the same m g y initial. And actually, let's just be specific. What is the initial height? If I'm talking about a meter stick, I'm looking at the height of the center of mass, which should be right smack in the middle. So in this case, the center of mass is at a distance of L/2. So my initial potential energy is mg L/2. And at the end energy is rotational kinetic energy. So 1/2 times the third is 1/6 ml squared times omega squared. And then if I solve for omega, what am I going to get? The masses cancel out. Oh, this L/2. I'm going to get the square root of 3g over L. That's horrible. Do this again. Omega squared equals 3g over L. So my omega is the square root of 3g over L. That's how fast the entire thing is rotating in radians per second right before it hits the ground. Now, if I want to know how fast is a particular part of the meter stick moving in terms of its translational speed. Again, remember, it's related by V equals R omega. So if I want to know how fast the end is a distance L away, which for a meter stick would just be a meter. So this would be L times omega, which is the square root of 3g divided by L, which I can just write as the square root of 3g times L. And then for this case, L would be 1 meter. All right, so that was, oh, then one last thing just in terms of kinetic energy of rolling. And again, this was a big recap, but I wanted to do this before we got to torque. If I have a rolling object, like I said before, kinetic energy of rolling has 2 pieces. It's got the fact that the center of mass is moving. I've got this translational speed, 1/2 mv squared, and the fact that it is also spinning as it's rolling. I have a rotational kinetic energy piece, 1/2 I omega squared. So I'm not going to do this particular example problem, but the only real difference when we're using conservation of energy is now I need to take into account, where is that one I want to look at? Oh, where is it? It's down at the bottom. Sorry for rolling past this. Okay, so let's just quickly look at problem 12b. And again, these problems are going to be more complicated than you would see on the final celebration or the quiz, just because of this online format. So in the figure below, a solid ball rolls smoothly from rest at a height of 6 meters till it leaves a horizontal section at the end of the track of a height 2 meters. How far horizontally does point A, how far horizontally from point A does the ball hit the ground? So here, we've done problems similar to this before, where instead of something rolling, it was just sliding down an inclined plane. But what I know is if something's moving horizontally initially, there is no initial velocity in the y direction. So what I'm going to do here is just use conservation of energy to get V right as leaving the track. So you would just use conservation of energy to figure out how fast is this ball moving as it's leaving the horizontal section of the track, and then it just becomes a projectile motion problem. And I think I mentioned this could be a really fun lab for lab 10. Most people have access to some sort of inclined plane, and hopefully everybody's got some kind of tennis ball or something there. If you have the ball roll off onto a horizontal section and then leave the horizontal section, you could use conservation of energy to figure out how fast the ball is moving right as it's leaving, and then projectile motion to figure out how far away it lands. Pretty cool little lab. But if you do it, keep in mind that when you're looking at conservation of energy, you have to include the fact that the ball is rolling. So the total kinetic energy right as it's leaving is not just 1/2 mv squared. I also have to take into account the rotational piece. So what I would get is 1/2 mv squared plus 1/2 I omega squared equals mg y initial. Or I would define my y equals 0 to be the height that it's leaving at. So my initial height would be 4 meters. So again, I don't want to solve this. The solutions are still posted, but I just wanted to sort of do a big recap before we start torque, which is the last thing I'm covering for chapter 12. Not going to cover angular momentum. It's a cool topic. You can read up on it, but just in terms of timing, I got to cut out some stuff. All right, I want to pause for a second. I've been talking for a while. I want to open it up to any questions I can answer on the little recap with stuff that I've covered so far for chapter 12. No questions? That was easy?
That was easy.
Yay! Okay, I'm taking off my recap. I'm not putting on my other hat because I don't know where it is. I'm actually really stressed by it. I love that hat. Okay, torque. I am just going to give you the equation for torque and talk about it without going through the derivation. The derivation is exactly the same as the derivation in the book, so I'm not going to just spend 15 minutes on it. All right, and here we go. So remember that every, a quick question. Let's check out the chat. Can't see chat. All right, I'll come back to that. If you remember, I was mentioning that every linear equation we've had has an angular counterpart. Well, the big giant equation that most of this course is based on is the sum of the forces equals ma, right? Newton's second law. And again, I think I mentioned this, you cannot derive this equation, right? This is discovered by Newton in pretty much most of physics 4A. Is based on the definitions of position, velocity, and acceleration, and the fact that forces produce acceleration. And then if you notice from work and energy, we started from Newton's second law and then derived some other forms of equations, but everything can be looked at using Newton's laws. Oftentimes energy, momentum, other things are easier. Well, the angular equivalent of force is torque. Just like forces cause a linear acceleration, torques cause an angular acceleration. So a torque will cause something that's not spinning to start spinning, to slow down spinning, to speed up spinning. It affects angular acceleration. The angular equivalent of mass we've already seen, that's our moment of inertia, which we write as I. And then our angular equivalent of linear acceleration is angular acceleration. And so Newton's second law in terms of torque and moment of inertia and angular acceleration is the sum of the torques on an object equal the moment of inertia of the object times the angular acceleration. This is Newton's second law for rotations. Newton's second law for rotations. Again, I'm not deriving it for you. You can look up the derivation, but it is the exact analog of Newton's laws, but for angular motion. Let me change this color, draw. Couple things about it. I'm not going to touch on this today, but it's going to be a lot what I cover on tomorrow. If you remember that we've looked at this system several times in several different ways, where I've got two objects connected by a massless, stretchless rope passing over a massless, frictionless pulley. And if the pulley was massless, then the tension on either side of the rope was the same. Well, what we're going to see is if the pulley's not massless, I cannot make that assumption anymore. And in fact, it's 100% not true. And just real quick, let me just tell you just a quick little thing. I'll go to bay here. Go down. So one, we're going to get to the torque definition in a second. But if I had, let's say, tension acting one, let me just call this T1, and I had tension acting here, T2. One, what we're going to see is that torque is equal to RF sine theta, where R is the distance from where the force is applied to the axis of rotation, F is the magnitude of the force, theta is the angle between R and F. If these tensions were exactly the same, where T1 and T2 were exactly the same, what we would see in this case is there would be no net torque. T1 would be causing this object to want to rotate clockwise. T2 would be wanting this object to rotate counterclockwise. And if the tensions were the same, the torque on each side would be the same. The sum of the torques would be 0, and the object would not rotate. So if an object is connected by a pulley which does have mass, the tension on each side of the rope is not going to be the same. T1 and T2 are not going to be the same. Okay, so I just wanted to throw that out there. We're going to talk about that on Thursday. Or what's today? Geez, I'm losing track of days. Today's Monday. We'll talk about that on Tuesday. So the question is, what affects torque? And where do I want to do this? I'll do this over here again. So let's say that I have a door. And this is just an overhead view of the door. And you know, the door is pivoted here, and I can cause the door to rotate by exerting a force on it. Now, how quickly this door rotates, its angular acceleration, is going to depend upon a few things. Well, the torque, but what does the torque depend upon? So here, what does torque depend upon? And so if you can imagine, let's say I exert a few different forces on this door. Let's go with green. So I'm exerting force, let's say F1 right here. I exert the exact same force, just call it F1 again, a bigger distance away. And in fact, let me exert the same magnitude force, but now at a different angle. And the question is, do these forces all produce the exact same torque? And the answer is no. You probably know from experience, well, one, why do they always put a doorknob on the other side of the door from where the hinge is? Because the farther away a force is applied from the axis of rotation, the bigger torque that force is going to exert. So you could, if you wanted to, have a doorknob right there. But the amount of force you would need to open the door would be much greater than if the doorknob was placed at the end. And in fact, you could actually make a cool little lab out of this for lab 10. If you could use a rubber band or spring or something to measure the force, you could look at forces being exerted at different distances from the axis of rotation of a door or something like that. So one, hopefully you realize that, let's say for this particular setup, let me call this force 1. The force that is exerted farther away from the axis of rotation is going to have more of an effect rotating this door than the force exerted closer. And the other thing that's going to matter is the direction. So if I have two forces, let's say just exact same distance, here's F1, and I exert another force, exact same spot, but at a different angle. You could imagine that the angle that the force is exerted at is also going to affect the torque. So the end result is the torque depends upon three things. So what does torque depend upon? One, it depends upon the magnitude of the force. Magnitude.
Pues come first then.
Let me just pause. Okay, magnitude of force. Two, distance of force from axis of rotation. And then three, so one, this would just be the magnitude of the force. So the magnitude of the force. One, how far away from the axis of rotation would be, we call that just R, where R is the distance between the force and where the axis is. And then three, it depends upon the angle between R and F. The angle between where the force is applied and R, which points from the axis to where the force is. And so the equation for torque, and here's why we needed the cross product, even though we're not going to do it much in this online format, is torque is defined as R cross F. Generally, we're not going to be using the cross product very much to calculate the torque, but what we are going to be looking at is the magnitude of the torque. And the magnitude of the torque, remember the magnitude of any cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between it. So the torque magnitude is equal to R F sine theta. And in this equation, theta is the angle between R and F when they're drawn tail to tail. Are drawn tail to tail. So for example, let me just make up two forces. And again, let's just assume that this is a door and it is pivoted about the end. I'm exerting one force, we call it F1. And let's just say it's a 15 Newton force. And let's say it's located an angle of, or 1 meter away. So that's going to cause it to rotate. Second force, F2. And let's just say that is 12 newtons. And the distance, let's make that, what does that look like? 1.4 meters. And the question is, what is the net torque? Couple things I want to mention first. Just like forces, where I look at the sum of the forces equals ma. If I have two forces acting in the same direction, those two forces add together. If I have two forces acting in opposite directions, those two forces cancel each other out, or they subtract. Well, in terms of torque, how do I consider a torque that's positive and a torque that's negative? Well, if you remember, any sort of counterclockwise rotation is considered positive, just like the way we normally measure our angles. Well, the same thing is going to be true for torques. So the definition of positive and negative for torques has to do with which direction that particular force would cause the object to rotate. So the little shorthand notation is this, and it just says torques that would produce a counterclockwise rotation are positive. So in this particular little generic example I just set up, F2 is going to cause this to rotate counterclockwise if that was the only force acting on it. So F2 would produce a positive torque. F1 would produce a clockwise rotation if it was the only force acting on it. So F1 is producing a negative torque. So if I want to know what is the sum of the torques, again, if I'm just looking at the magnitude, we're not worrying about direction in terms of the cross product. Counterclockwise torques are positive, clockwise torques are negative. So for F2, since it would produce a counterclockwise rotation, it's going to have a positive torque. So it's going to be plus R2, F2, sine of theta 2. And then F1 would produce a clockwise rotation. So it is a negative torque, and it's going to be R1, F1, sine theta 1. Now, important thing is when I'm looking at the angles, remember you always draw angles or vectors with their tails touching. And one thing I need to be specific about the R vector. R, it points from the origin or points from axis of rotation to where the force is applied. So let's just look at each of these forces. So again, let me change colors. Draw, let's use red. My R1 vector that I would use for calculating the torque from force 1 is I draw a vector starting from the origin to where the force is applied. So this would be my R1 vector. And then R2 would point, again, from where the axis is to where the force is applied. And if I want the angle between if I want the angle to calculate torque, it's always the angle between the two vectors if they're drawn tail to tail. So one, I guess I never told you what angle this F2 is at. So let's just say this angle here was 30 degrees. So the angles I would use for calculating the torque is I draw the two vectors together, R and F. Theta is the angle between the two. So for F1, my R vector points to the right. This would be R1. My force vector points straight down. Remember, if I'm getting the angle between two vectors, I always draw them tail to tail. So in this case, my theta 1 would be 90 degrees. And the angle is always the smaller angle. It's always less than 180. So in this case, the angle between R1 and F1, 90 degrees. Now, how about the angle between R2 and F2? That's a little bit trickier. R2, again, is pointing from the axis of rotation to where the force is applied. That's not R squared, it's R2. Hey, R2, R2D2, happy Star Wars Day. R2, and then F2 is applied up at an angle like this. So the angle that I would use for theta 2 when calculating the torque would be 120 degrees. Okay, so if I go and actually calculate this torque, let me just do it right here. The sum of the torques then, I've got my R2, which was 1.4 meters, times F2. Did I make up a value for F2? F2 was 12 newtons. Times the sine of the angle between them, which would be the sine of 120 degrees, and then minus R1, which was 1 meter, times F1, which I said was 15 newtons, times the sine of 90 degrees. Okay, so whatever that works out to be, I'm not going to just do the math. I just wanted to emphasize a couple things. So important things. Torque, R, F, sine of theta, where theta is the angle between R and F. R is a vector that points from the axis of rotation to where that particular force is applied. Torques that produce a counterclockwise rotation are considered positive. Torques that produce a clockwise rotation are considered to be negative. And that's really torque in a nutshell. And so what we're going to now see, well, we'll probably do this tomorrow, but the sum of the torques on an object equals I alpha. And so if I want to, so kind of like what we did with Newton's second law, you could start to combine Newton's second law and kinematics. So I could use the sum of the forces on an object to determine the object's acceleration, and then use kinematics to figure out how fast the object is going or how far it's traveled or final speed or something like this. For Newton's second law of rotations, similar is what would happen is I would use the sum of the torques to figure out what the angular acceleration is. And then from the angular acceleration, I could tell you how quickly it's rotating after accelerating for some period of time, something like that. Okay, let me just do a quick little example problem that we'll do on tomorrow, but I want to just set it up. Quick question for you to think about, and then I think I will end the lecture portion of today. I'm going to start tomorrow looking at problem 22. It says the 20-centimeter disk in the figure can rotate about an axis through its center. So here is the axis of rotation. What is the net torque about the axle? So I've got 4 different forces. For each force, I first want to think about, would this force cause the object to rotate counterclockwise or clockwise if that was the only force? If that force would cause the object to rotate counterclockwise, that is a positive torque. If a force would cause an object to rotate clockwise, that would be a negative torque. So looking at these, well, quick question for you. How many of these are producing a positive torque? How many of these are producing a negative torque? And are any of them producing 0 torque? Take just 30 seconds. I'll talk about this in 20 seconds, and that'll sort of be the end of today's lecture, and then I'll open it up for office hours. And just to be clear, let's label these. So let's just label this one force 1, this guy force 2, this one we'll call force 3, and this one force 4. Question is, which of these 4 forces are producing a positive torque? Which of these 4 forces are producing a negative torque? And are any of them producing 0 torque? And let's just write the answers here. So positive torque, a negative torque, and no torque. Well, are any of these producing no torque? Would any of these not cause the object to rotate at all? And the answer is yes. Force number 4 right here is not producing any torque. And mathematically, what is the angle between the force and the r vector? Well, r points from the axis of rotation to where the force is applied. It's pointing in the exact same direction as the force is. And so when I go to use RF sine theta, for this particular force number 4, theta is 0, and so it doesn't produce any torque. So force number 4 in this particular problem would not produce any torque. Just real quick, what would force 4 do? If this thing was free to move, it would cause the center of mass to accelerate. Now, torque is positive if it causes a counterclockwise rotation. So force 2 would cause this disk to rotate counterclockwise if it was the only force. Force number 3 would cause this disk to rotate counterclockwise if it was the only force. So forces 2 and 3 in this particular example would produce positive torques. And then force 1 would cause this to rotate clockwise it would be producing a negative torque. And then what we'll do is just on tomorrow, we will start with this and actually mathematically calculate what is the net torque. One last thing, let me end on. The equation for torque, RF sine theta, I didn't mention the units. The units of torque have to be the same as the units of R times the units of F. So the unit of torque is the Newton meter. And even though a Newton meter is equivalent to a joule, you never, ever, ever use joules as a unit for torque. Kind of just like kilogram meter per second is equivalent to a Newton second. You always use kilogram meter per second for momentum. You always use Newton second for impulse. For torque, you always use Newton meter as a unit of torque. You never abbreviate it as the joule. Woo! Okay, I think you meant 4. Why is one labeled no torque? Oh, did I make a mistake? No torque. Oh, you're right. No torque should be number 4. Let me just share that again. Boop. Share screen again. Yeah, so I had mislabeled this one as number 1. Force number 4 is not producing any torque. And in fact, anytime you're exerting a force along the axis of rotation in direction, so if I had a door and I was exerting a force in this direction, that particular force is not going to produce any rotation. That force is not exerting any torque. So yeah, I made a mistake before. Thank you. Okay. Lecture portion done. Office hours portion, bringing it in. I have hang out here until about 12:30 if people have any questions about what I just covered, or lab 10 questions or anything like that. Keep in mind torque, last thing I'm covering from chapter 12. Tomorrow I'll talk about it a little bit more and then do some example problems, and then bam, that's it for chapter 12. Thank you everybody who joined me. Hope you are staying healthy, and 2 weeks, we can do it. Woo! Thank you everybody. So yeah, I'm gonna hang out here for about 20-25 minutes. If you have questions, let me know. If there's no questions, I'm gonna sort of mute the video and
Hey.
Yes, Maria, what's up?
Hey, Joe. I was wondering if I could just kind of talk through an idea with you for my lab.
Most definitely.
Okay. So I pulled out a little spring from a pen.
Okay.
And I was going to try and first try to determine K using like different masses. And then after I determined K, I was going to see if I could, I don't know how, oh yeah, using conservation of energy, maybe figure out how far I could launch something on some ice.
I love that idea. So you would first figure out what K is, and then compress something a known distance against the spring, let it go.
Yes.
So here's the question. So if you get K, then you can figure out the initial elastic potential energy 1/2 K delta X squared.
Yes.
But then what are you going to compare that to? So like if you could compare it to the kinetic energy being launched once the spring is no longer stretched or compressed, but how would you go about calculating what that kinetic energy is? That's the part that might be tough to think about. If you could somehow, let me share a white screen now that I'm thinking about this. Share screen. I don't know if you could work this out somehow because they're sort of thin springs, but you want to be able to compare the initial elastic potential energy stored in the spring to some final energy. Could be the kinetic energy right after the spring launches it, or if you could launch something straight up, then you could compare the initial elastic potential energy to the gravitational potential energy. So my thought would be, oh, this turned off. Hold on one second.
Maria. Yeah?
Pizza's here.
Okay, I'll be there in a second.
Pizza? So if you could somehow put like a little rod or something in between the spring, and then, again, you'd have to play around with this. Oops, I can't erase, eraser. And then somehow use, yeah, you'd have to think about this, but then you could compress the spring a certain distance and have a mass that would sort of fit on this stick or something. So
Uh-huh.
once you figure out K, then you would know what this distance delta X is. So you could say, okay, my initial elastic potential energy is 1/2 K times delta X squared. And then if you let this go, then it launches this thing to some height. Then you could use this height to figure out if the final gravitational potential energy at the highest point equals the elastic potential energy stored in the spring. So that's one possibility. And in fact, I just talked to somebody who's doing something similar, but they're using the spring to compare the mass of an unknown object. So they had a cell phone that they could look up the mass, the known mass of the cell phone. So once you calibrate the spring and you have the spring constant, then you could hang a known mass or an unknown mass off the end and get the mass of that object by looking at how far the spring stretches and compare that to the known mass. Just sort of as another example. But just keep in mind, if you're going to use a spring and look at something with energy, you have to be able to measure either the kinetic energy after the spring is fully extended or the gravitational potential energy at the highest point. And that could be challenging just to measure, you know, accurately measure heights.
Okay, well, what about if I did, instead of like, I was thinking like, you know, how in the examples ice was always like frictionless?
Yes.
Well, I was thinking about maybe, you know, seeing what the coefficient of friction for ice would be based on like the final energy being 0 of something stopping on the ice. The
Yeah,
work
you can try that.
ice, and
One
then
thought I had too is, let's think, if you, you could also try and look at, you know, if I compress the spring twice as much, it should have 4 times as much elastic potential energy, which means 4 times as much kinetic energy when it launches something, which would be twice the speed. So you could look at, if I compress the spring twice as much, how much farther does it go until it stops? And does that make sense? So, you know, the work done should depend upon how far the friction is acting. And so if something has twice as much kinetic energy to start with, is that going to result in it moving twice as far before friction removes all of the energy? So there's definitely things that you can play around with. What I would say is you need to try a couple of these just to see how challenging the actual setup is.
okay.
And I'm expecting people to, you know, try something, figure out it doesn't quite work, try something else, which is one of the reasons you have 2 full weeks to do this.
Okay. Sounds good. Thank you.
You're welcome. Enjoy the pizza.
I will.
Hey, Raph.
Hi, Joe. I also want to run you through with my idea for the lab.
Okay.
So I got this like rubber bungee cords for working out.
I have
Like
those ones.
stretch.
Yeah.
And they have like labels of how much, I guess, how much weight they're equivalent to.
Oh, hold on. Let me mute this for somebody's.
Sorry, that was me.
Oh, okay. No, cancel that. Okay, go ahead.
So they have labels of how many pounds I think they're equivalent. So they have like 40, 50, 30, 20 pound bungee cords. But when I pull them, I don't feel that weight enough.
Yeah, I was just thinking of that. I have those too. And like when I used to buy them for working out at home, it would not give, I don't remember them giving like pound equivalent, but you know, there was just light, harder, you know, easy, medium,
Right.
hard. Because if you could somehow model this as a spring, it's probably not. How much force you need to exert is going to depend upon how much you're stretching it.
Yeah, so my idea was like to, because mine does have like the pound measurement. So I'm wondering what that measurement is for them. It's like a force max or something.
Oh, that could be. Because it can't be just how much force you need to exert to stretch it, because that's going to depend upon how far you stretch it.
Right.
So I
And
don't
I do have
know
a
if-
weighing scale for like luggage and stuff. So I could use that to like measure how much actual, roughly, how much strength I'm using, how much force I'm using.
And so what's the theoretical idea that you're testing? So like for all of these labs, I'm hoping people have a theoretical value of something that they can test, and then you can do enough measurements to get a standard deviation, standard error, and so on. It may not be
Right.
possible for everyone. So, but like, what's your big idea of what you're going to test out? It's just what that
So my
is?
idea is trying to find roughly a K for the elastic, and kind of chart the strength over length, and see where that 40-pound, if that 40-pound mark even hits anywhere there, if it's like a max strength or not.
Right. And you have more than one of these?
Yeah, I have a few with different strengths though, but I have like 6, I think, or 5.
Oh, so then it might be interesting to try and do some sort of comparison. So, you know, you might want to just think about this more to flesh it out, but you take one of them, you do some measurements on it, and you figure out for a 20-pound what they say it stretches this much. And then see if you can predict from that, if you move on to one of the ones that's rated at 40 pounds, what the result of that's going to be.
Mm-hmm. Okay, that's interesting. Yeah.
But yeah, I like the idea of that, but then trying to make a prediction and test it out.
Okay, I'll better my prediction then. But I think that's a valid lab.
Totally, yeah, that sounds good.
Okay. And I still need to email you with the details and stuff, right? Is it by Wednesday, the due date for emailing?
Yeah, just something like this, or even, you know, I've talked to you enough, just send me a little brief description.
Okay, just a reminder.
But I just want
this.
to get people to think about it before the last minute, because having, you know, tried to create labs in the lab with all the equipment, you never realize all the little things you need to correct for until you actually set it up and start doing it. So I want people to think about this early enough that if there's any problems, they can come up with something different.
All right.
All right, thanks, Jeff. Yep, Zane, you got a question?
Yeah, so I have, wait, can you hear me?
Yeah, I can hear you.
Okay, so I have this digital torque wrench, and I was wondering,
Torque wrench.
yes,
Ooh.
and so I was wondering if I have like a scale, a digital scale, and I pulled on it at an angle, could I try and find the angle between what reads out on the digital torque wrench and the force I'm applying?
What I would think of a child, So you're wanting to use a known force and the results from the torque meter, or whatever it is, to get the angle?
Yeah, to try and solve for the angle I'm pulling.
I might try and do something different where I might try and, you could do that. And I like the idea of taking something that we're studying now, torque, or you could also, rather than try and measure the angle, just try and exert a known force by hanging something of a known mass off the end, a known distance away, and seeing whether the torque that you calculate matches what the digital readout is. So like it might be easier if I was doing this. Let me just share this, clear all drawings, is, you know, everything here is a rod. So here's my torque wrench. If you had objects that you had a known mass, so like you might be able to hang something straight off the end, in which case you know the angle is going to be 90 degrees when this thing is just still horizontal like that, and then see whether the torque that you get from RF sine theta, how that corresponds to the reading that you're getting from the, what do they call it, a torque wrench? So it's got a little digital readout on it.
Yeah, so I can do like Newton meters, I can do kilogram per meter, I can do foot pounds, I can do a few other.
Yeah, so I think that would be a great idea to flesh out some. So my recommendation would be exert a known force, which you have to figure out exactly how to calculate that known force, at a known distance away from the axis, and then see whether the calculated torque matches the torque that the torque wrench gives you.
See, that's actually what I was thinking of doing initially, but I thought it might be a little too simple. But
well, I wouldn't want you to just like, all right, I think the torque's going to be 10, it was 9, I'm done, right? So fleshing it out a little bit more, where you're doing, you know, enough trials that you can get some sort of something that you can test the theory out with.
Because initially too, I also thought maybe like doing certain distances away from the axis and hanging weights, and then like maybe comparing different weights, like maybe twice the weight but half the distance, and comparing different
Oh yeah,
readouts.
I like that idea too. So, you know, the same force, yeah, if you do twice the force at half the distance, that should produce the same torque as, you know, the force. You can understand what I'm saying, right?
Yeah.
A certain force at a certain distance should produce the same torque as twice the force at half the distance. So you can look at those sort of combinations of 3 times the force at a third the distance, 2 times the force at a half the distance, something like that.
Would that be acceptable?
It would be acceptable.
Okay. That sounds
Yeah,
like a
I mean,
plan
part of
then.
this is just to get out thinking outside the box, and I want to see what people come up with. And yeah, so that's totally acceptable.
Alrighty. Thank you.
You're welcome.
Would you like me to email you later about that just to confirm it, or?
Yeah, just send me like a little 1 paragraph, couple sentences, just exactly what you're going to be testing. So we've talked a little bit about different ideas. Just let me know exactly which one you're going to do.
Alrighty. Thank you.
Sounds good.
Joe, I have a question regarding video trackers.
Regarding video trackers?
Yes, is there any one specific video tracker you recommend we use?
You know, I've never used any video trackers. So John recommended, there's one that actually an old Cabrillo instructor wrote called Tracker that I've never personally used. And so I hate to tell you this, but I can't give you any meaningful information out of them. I've never used any video trackers. So the one that is available through the Cabrillo sites, or you could just search for Tracker, is fairly well written. But like I said, I've never personally used it. But in general, what you're doing is you're filming something like throwing a ball in the air, and you can import the video into this video tracking, mark the position of the ball at certain times and things like that. And then you can use the tracking program to analyze a bunch of different things about it. So let me just say, if you're going to do that route, that's great, but I can't be much of assistance in terms of getting the software set up or anything like that, because I haven't used it. However, John Welch has helped modify Tracker. So if you did want to use it, he has a ton of information. He could be a great resource. But personally, I haven't done any video tracking software programs myself.
Okay, sounds good.
And do you have an idea like what you want to use the program for? Like what experiment are you going to do?
Well, I originally thought, since I have BB guns, I kind of thought maybe I could use, I don't know if you've ever seen those little blocks that soak water in.
I didn't catch that last sentence. You were breaking up.
They're like little green mushy blocks that soak up water to put flowers in, and when they're dry,
yeah.
they're relatively light.
Yeah, I know what you're talking about.
So I thought of shooting one up with a BB gun, but that didn't work. So I'm thinking of doing it maybe with a soda can, or maybe even switching it up to dropping a ball and figuring out how much energy, sound, and heat with heat bounds.
Okay, I like the idea of shooting something. Here's what I would just suggest is you want to try and come up with a testable theory. So if you knew like how fast the BB gun shot the bullet, and you knew the mass of the BB, you could figure out what the initial momentum of the BB was. And then if you could find something that the BB would stick in, then you could maybe use conservation of momentum to figure out how fast they're both moving afterwards, and then do some sort of conservation of energy calculation. So it sounds like you have a good start, but I would think about coming up with a testable theory that you can get enough data to see whether or not you were right or wrong.
Okay. Or another one I thought of is using a Nerf gun to find the constant of the spring inside of the Nerf gun that uses to shoot out the dart and try to figure out how far it lands.
You could do that. My only first thought is those Nerf guns are going to be highly affected by air resistance.
Oh.
Right? Because they're very light, and trying to model that, I mean, you could try it, but your results are going to be awful, just probably because air resistance, taking that into account for a Nerf gun, I mean, that's something that's going to have a lot of air resistance.
Right. Okay. What is John's contact information? I'd like to see if he knows of anything, any tracker that I could use.
Yeah, it's JOWELCH@cabrillo.edu.
Okay.
All right, well, good luck. Let me know if you have any other questions as you're getting rolling with this experiment.
Okay, thank you.
You're welcome.
I have a question. Is everybody?
Right.
Hi, it's Sheriff here. So I was driving the other day and I ran out of gas on a kind of an incline, and my car just barely coasted into the gas station. And
Are you going to do that again as an experiment?
yes, and I was thinking, well, what is the force of friction that's slowing my car down? Because I was like, it was like, come on, guys, you can make it, and it barely did. So I was thinking of putting my car on a hill. There's a hill by my house with a long straightaway that nobody drives. So I was going to put my car in neutral, and I have a digital protractor. I can see the angle of the hill and the distance up the hill to get the height, so I can get the potential energy. I was going to use an average for the mass, kind of Google foo.
Right.
And then I could figure out the kinetic at the bottom, and then using the kinetic at the bottom, I could figure out what the force of friction was, right, when the car stops. And then I was going to do 10 trials of just let the car go down the hill, see how far it goes, and then see the difference in what the car friction is versus how far it actually went. Am I explaining this right?
I think so. So you're first going to try
the theoretical would be like without the car friction, how far would it go? And then I would actually test it, and I would see that, oh, actually, it's not going as far as it should have gone.
And then what are you going to get from that? You're going to try and get like a coefficient of friction or something like that?
Coefficient of friction. Yeah, and then I was going to try to get the coefficient of friction.
Yeah, I like that idea. So you get maybe some kind of coefficient of rolling friction, and then depending upon the tires, you may be able to look up a theoretical value. I don't know how well they are, but most cars or most tires, you can look up for a Goodyear tire, this tire with these kind of road conditions, this is the coefficient of static friction, coefficient of kinetic friction, coefficient of rolling friction.
Now,
so I don't know 100% that that's true, but ideally it'd be great if you could have a theoretical value that you could look up to test it on. But if you don't, I love the idea of that experiment. And actually,
I was just curious about how far my car, because then if I know the coefficient of friction, then I can know how far up a hill I need to be next time I run out of gas to get a certain distance. Right?
Or you could just keep your car filled up.
I mean, there's that too. But so if I can't figure out what the theoretical friction should have been, is it still okay to do the?
Yeah, no, I like the setup.
Figure out what the actual friction is.
Yeah, no, that's creative. I like that idea.
Okay, cool. And so then we just have to send you an email by Wednesday. Is that what it was? I missed that part.
A quick little, description of what you're doing in terms of, just kind of like what you said. Okay.
And then Shinji is my partner in this. We were kind of doing this together. If that's 2 people is okay, right?
Yep. And as long as, if you're going to do a video presentation, you're both there, or you each do your own video presentation, or you each write up your own formal report.
Totally. Cool.
Awesome. I look forward to seeing it.
All right. Thanks, Joe.
All right. Take care, Sheriff.
Hey, Joe.
Hey, Marco.
I was planning on doing the ball drop one, finding the energies, but after that, could I just simplify Sheriff's experiment and just take some wood and then look up the value, the friction coefficient that it should be, and then try and test for that, by sliding it down a wood ramp, just a block or something.
You wanted to do 2 experiments? Is that what you're saying?
No. I'm thinking if I were to just take a wood ramp, I don't know, a sheet of plywood, or I don't know, just a 10-foot wood ramp, and then take a wood block and then look at the coefficient of friction that it should be, and then just perform tests to see that if it would get anywhere near that, and then
you could do that. My thought is, so you need to use either forces or energy or something like that, but you're probably going to need a way of measuring either what the acceleration is or what the speed is. So, you know, let's say you have something on top of an inclined plane where there is friction. You want to be able to predict what the speed should be given the coefficient of friction, or from the speed at the bottom, and you know that it started from rest, you could do a calculation to get the coefficient of friction. But that means you need to be able to somewhat accurately measure the speed at the bottom.
Okay, so then once I find something to do, like measure the speed at the bottom, then that would be a pretty valuable experiment.
Yeah, that sounds cool. I like that idea.
Okay.
Just so you know, classically measuring friction is challenging. I don't want to discourage you. Just know your results may not be super consistent. I don't think I've ever gotten a really good lab for friction. Like trying to just measure the coefficient of friction, it's challenging, but totally worth it. And you know, I'm not marking people off if they design this great experiment and the results weren't consistent. That's part of doing science.
Oh yeah, I've learned from my science career that the percent error is always really high for me. So.
Oh yeah, and this is, you know, a lot of times when John and I try and develop a lab, all little things come up that you never thought of before until you actually set it up and start doing it. So I like this lab just because it's real science, and it's even more real science because you're just using stuff that you need to collect out in your house.
Right. Okay, sweet. So then I'll send you an email by Wednesday.
All right, sounds good.
All right, thank you.
You are welcome.
Hey, Joe.
Yes, hey, what's up, Omar?
I was just wondering, where can we find like all of the information for our lab, like kind of like our design?
Just what's expected in lab?
Like, yeah, is it like in your website, like something that we kind of have to like follow?
Yeah. Let me share the screen. So in the online physics online resources, where is it? Labs. So here I've got a little sort of PDF of some of the different kinds of experiments that you could do. And then there's a little video here. I think it's like a 10-minute video on YouTube, just talking about sort of the setup of the experiment and things like that.
Oh, okay.
So yeah, check those out.
Yeah, for sure.
Yep. Any other questions for anybody? If not, I'm going to sign out for the day.
Is it 100% going to be like formal lab report or video, or like?
So you have three choices. You can either do a formal report. Next Wednesday, you could do a 5 or 10-minute Zoom presentation just live while John and I are on Zoom. Or you could record a 5 or 10-minute video and then send it to me. So those are the three options. They're all equivalent. My preference, I think it'd be great if everybody could get on Zoom and do it with other people watching and asking questions, but that may not be possible. So those are your three possibilities. Zoom presentation, recording a video yourself and sending it to me, or doing a formal report.
Sweet.
At what time would the Zoom presentation be?
The Zoom would be next Wednesday.
Like,
I will send out some times. We'll probably have 3 one-hour times when John and I will be available to do it.
Okay, gotcha.
All right. Well, thank you guys for joining. Have a wonderful day, and I will see you tomorrow.